are. That's all GPS is doing. But it has to know where the positions of the satellites are. And again, all these satellites have to have clocks that are synchronized extremely well in order to tell you, which side of the street you're on. This time changes depending on how much gravity you have. How much gravity you have depends how close to the Earth you have, or close to a massive object. So the time on the GPS satellites is going more slowly than the time down here on Earth, or the other way. So it's faster there, slower here, because the time is slowed down in the gravitational field. So we actually have to adjust for the time the GPS satellites have because of the gravity of Earth, because of that gravitational impact. General relativity, not even special relativity, general relativity. That impact on the way clocks go is not only measurable, it's critical for being able to navigate the streets around here, especially for counting. So that's the point is these things are not just theoretical, they're not just ideas. They are things that we actually need in order for modern life to work the way it does. If you want to go back to 1900, then you can forget everything. But for the most part, this stuff really does have not just a practical, obscure application, not just measurable, but it really is what a lot of our technology depends on. So what I want to leave you with is the idea of what I was trying to do with this class. Really, to show you that, first of all, that there are answers to questions. That's where I started with at the beginning. You go through life, there's a lot of things, and there's, you can say why. And we forget to say why because we're now older. But I thought of doing this when my oldest son was 5 years old, and would say, well, why this, why that? And I realized I can answer those questions. Those questions have answers. And that was the first thing I really wanted to convey. The second thing, almost as important, is that it's not impossible for you to understand those answers. Not as a practitioner. You're not going to derive mathematically these things. You couldn't with enough tutoring. But just to understand that it is possible, and I don't expect that throughout the 6 weeks here, as I've covered 100 years of physics, you get everything, whether you can understand everything as I say. But to be able to see that there is a progression, that given the time and attention, you could sit down without even having to know any math, and be able to get at least a conceptual understanding of why everything is and how everything works. That's really what I wanted to convey. And finally, the third thing is that as a physicist, when you go to the eye doctor, you say, what do you do? So physics. Oh, I hated physics, I was terrible at it. And that's okay to say. Nowhere do you go in life and people are proud of the fact that they don't know who Shakespeare is, or that they've never heard of the Iliad or the Odyssey. You can't say those things as an educated person. You may not have read the Iliad, maybe you read the Cliff Notes for the Iliad, but you're not going to go around complaining, oh, I hated classical stuff, it was, you might say Latin was hard, but you're not going to say, I never heard Cicero's name before. But in physics, that's okay to do, right, in our culture. It's fine to say, oh, I don't know any of that stuff. It's okay to open the newspaper and see that article on the new particle accelerator, and I'm not going to read it. And giving you that understanding that it is important just to how the world works, but that you can understand it, and it's, all of us can understand is really what I was trying to do. This was quite a bit of an experiment. I've never actually taught a class in this kind of structure before. I realized I've never actually spoken to an audience that didn't have to be there for one reason or another. High holidays is easy, but certainly if I've got a final, you have incentive. So I want to thank everyone for coming out, for sticking with it. You all graduate with flying colors. Questions as they come up throughout the rest of our lives.
Since you were talking about everything, and there was that movie, The Theory of Everything,
right,
about Stephen Hawking, did he because I couldn't understand, even though I saw the movie, right, did he somehow tie all of these principles into one principle?
The two phrases, one is grand unification theory, which is connecting all the particle physics stuff together, strong, weak, and electromagnetic. That's grand unification. And then they already used up grand unification when they needed to connect gravity. They had nothing else to say. So they said theory of everything, which is TOE for short. That's the dream of, the other book is Dreams of a Final Theory. That's the dream of being able to connect the relativity and gravity stuff to the rest of the standard model of particle physics. Has not been achieved. Hawking's not going to get to it. None of us are, but
you came close?
Not particularly. You get into the things that can't be tested. You get into string theory, you get into more exotic theories. There were 11 when I was in grad school, and they decided they needed 17 dimensions in order to figure out how to make the stuff work, and they're not there. They do work on it. The problem is coming up with something that you can actually do an experiment on, which, if you really do have the right theory, there's going to be ways to test that. That's, I mean, connecting gravity and these other things, it's just not.
So what Hawking did is totally theoretical, it's never been.
He's a theoretical physicist. Everything he's ever done is theoretical. It's his domain. But if you want to do, the theory that applies to, there's been a split in theoretical physics, theoretical particle physics between the theory that's really out there and doing profound things, and then the stuff that you can actually connect to, because they got too far ahead of what you do experimentally. So theorists that work in stuff that is testable are now called phenomenologists. They're still theoretical physicists, and it's less sexy, but they can actually justify what they're doing. They've actually split up where they are in the department as well. The string theorists are off in one corner, and literally a different office block is where they put the other guys. They do have tea and cookies together every day at 4. Which show that any physics department in the world, if you're ever hungry at 4 o'clock, there's tea and cookies. Everywhere.
The Israel action thing is in the library upstairs. They're just starting if anyone's going.
You can